This is a demonstration video of our work, MPPI DBaS, Safe Trajectory Optimization with Adaptive Exploration. In trajectory optimization, Model Predictive Path Integral, MPPI, is a sampling-based model predictive control, MPC framework that generates optimal inputs by efficiently simulating numerous trajectories. In practice, however, MPPI often struggles to guarantee safety assurance. In the standard MPPI, constraints are assessed using weighted indicator terms. These costs impose an impulse-like penalty upon constraint violation, serving as a hybrid approach between hard and soft constraints. However, this method does not provide any risk information until the constraints are violated, posing challenges in trajectory optimization. Also, MPPI faces challenges in balancing efficient sampling. On one hand, setting a small exploration rate makes it easier for MPPI to evaluate and decide a fine trajectory among the samples in a loosely constrained task, as most trajectories are in close proximity. On the other hand, setting a large exploration rate increases the likelihood of finding a path through a narrow gap in a tightly constrained system environment scenario, sacrificing precise tracking in free space. We here propose the novel MPPI DBaS controller with two key enhancements. Firstly, to enable the controller to maintain safety with a shorter planning horizon, we integrate barrier states into the system's dynamics, thereby addressing the safety concerns as part of the states under control. Secondly, we introduce an adaptive exploration mechanism of sampling trajectories. Given that the barrier state ensures the safety of each sample trajectory, a high running cost would evaluate a closer proximity to obstacles and a higher risk of collision. In return, this guides our exploration strategy. To avoid the local optima commonly met without a fine-tuned safety cost, we would employ a higher exploration rate that encourages more diverse trajectory sampling, yielding roughly optimal paths. Subsequent action steps, informed by this initial broad search, can then commence with a lower exploration rate, leading to a more precise near-optimal solutions with safety assurances. The key formulation and algorithm are stated here. For more details, please refer to the paper. In this section, we present simulation results comparing the proposed MPPI DBaS controller with the standard MPPI on a path-tracking vehicle. The vehicle is modeled as the following discrete-time nonlinear Ackermann steering model. This slide demonstrates the baseline MPPI performance, which meet a variety types of failures. This slide demonstrates successful smooth navigation and adaptive exploration of the proposed MPPI DBaS. The detailed comparison between two controllers are presented in the right table. The proposed algorithm significantly enhances the success rate with lower tracking error, compared to standard MPPI algorithms, particularly in scenarios with strict constraints. In conclusion, we have developed a novel MPPI DBaS controller that integrates a barrier state into the dynamic system, thereby ensuring hard safety capabilities, surpassing the standard indicator function used in standard MPPI. Additionally, we have developed an adaptive exploration mechanism for sampling trajectories, which facilitates more extensive and varied sampling when approaching obstacles. Thank you for watching the video.